Hello and welcome. I'm starting a new series of videos. I've been doing my underground science videos for like a year, a little over a year. And along the way, I did all these on, this is my Baja BC playlist. I noticed the number, I'm on 370 now. Notice So we got a bunch of them. Probably the most relevant to Baja BC are 229 and 232. But down here, I started to come back to it. So my most recent episode is 370. I've been looking at large igneous provinces, this playlist. So basically starting at 360 to 370. I've been looking at large igneous provinces, and it brought me back to Baja BC. And I'm like, I haven't really looked at that in a while. So I started watching them again, watching ones from Nick Zentner's channel here. So I've watched all these, as you can see. Possibly restarted some. But, yeah, so I was like, if I just watch them, it's not going to be as useful maybe as if I did what I have done in the past and just reacted. So I had this idea to just react to this entire series. I did that before with the Alex Jones defamation trial, where I reacted to the entire first trial. Here's a bunch of my playlists. So I got a bunch of playlists. One of them is Baja BC, and one of them somewhere is the Alex Jones defamation trial. I also did it with the Malcolm Bendel lectures. There's that one. Not that it matters, but I'm sure people are like, what? I didn't expect to be talking about that, so pardon me. So, Baja BC, what is this? If anyone who doesn't know what I'm talking about, don't worry, we're going to go into it a little bit. How did the Rockies form? And if we just Google it, it says, well, this one doesn't really explain what I was looking for, but the Rockies formed at a time in which a number of plates began sliding underneath the North American plate, according to plate tectonics. The angle of subduction was shallow, resulting in a broad belt of mountains running down western North America. The thing is Baja BC, what this is about is saying, wait a minute, there's material from Baja, California, down all the way down here. There's material from here able to be deciphered by paleomag. So paleomagnetism is the study of magnetic fields recorded in rocks. So we're going to go into some stuff, but just essentially the paleomag data started to indicate, in some instances, 3,000 kilometers south of where it was when the paleomag was imprinted into the rock. So this record of the Earth's magnetic field at the time of the formation of the rocks, when this magnetic field of the Earth was imprinted into the rocks, has since moved up here, but still contains that data where it formed down here. So it's able to be suggested, at least. So we're going to go through the data. So that's called translation in geology. In the geological world, kinematics is concerned with the change in location, translation of a body of rock or parts of a rock, its rotation, its distortion, and dilation. Okay, so Baja, BC. I found out from Nick Zentner, his channel, which is awesome. And he has all of these. When I watched the Baja, BC, I did not read all of the accompanying papers. So we're going to watch A. But before we do that, we're going to go through these papers. Sorry if that's a little boring to anyone, but if you watch my channel, you know that I do that a lot. Like, especially recently, a lot of my videos, like these ones have all been papers, like articles. There's one, there's one, there's one, there's one, there's one, there's one. Here, notice this one, Atwater. Fracture zone traces across the North Pacific quiet zone and their tectonic implications. So in 370, we came across Atwater. We're going to come across Atwater again in this video. It's just kind of interesting, this paper actually. Tanya Atwater et al. And, okay, so let's close these so I understand they're done. That's can close that too. Close that. Close my channel. Okay. So, A. Why do I have this? We'll get back to that. What the hell was that? I'll explain. So this is a paper called Anomalous Paleolatitudes in Cretaceous Granitic Rocks. Sorry, I'm just going to jump into it because this video is an hour and a half. So I'm going to have to play it fast. And we're going to determine, we'll see, you guys will find out, as I will, if I can do all of the papers and the reaction to the video in a single video. It's already 12:30 at night almost here, so I probably shouldn't, but I would really like it to be in one video. Unfortunately, the first one, I kind of need to give it a little more information, and going forward, I'm probably going to jump into things real quick, so highly recommend this be watched in order as well. I mean, just in the way as his are in order. Like, there's going to be a sequence of events in terms of things talked about, so, like, odds are anyone watching the future ones without watching this one won't be quite as acquainted with the details. Okay, and I mean, that's right. So it's important to understand, before we do this, I personally do not believe the Earth functions under plate tectonics. I believe the Earth functions under what's called Earth expansion, more so that it expanded from specifically 541 million radiometric dating to the Holocene was a phase of expansion that in this video titled Earth's Undercurrents, hopefully I link this one in the description below, I use the magnetic anomaly map of the Earth, interpret the blue as low intensity anomalies in the magnetic anomalies of the magnetism of the Earth. I interpret the blue as regions that current flowed below the crust in the Earth's expansion process, and the pink as regions that basically that flow of current ran into itself in other places or like along itself and created a compaction of material that led to an actual physical mound, like a barrier, so walls like under the crust though, that then are able to be traced. So I traced it and said these are the currents that flowed out this way. It went over into North America, did something of that nature. It also went eastward, went up to the pole, interacted with the North American structure, went around it, went up this way, went across into Asia, split this way. Notice the structure. Like it's bending around this, but splitting though, like so. It goes back up there, forms a terminal up there, goes in here and induces the Siberian traps, forms a terminal up here, interacts down this way, goes over into South America, goes through South America, which then interacts with the first current going westward under Europe over here. So then goes south, causes a division of that current to go southward, which then flows along the eastern region of Africa, interacting with this cross current. All this is going on like in different magnitudes, but generally happening throughout the process mostly. It's just that's like at certain points this really becomes pronounced. But it interacts across this way with the East African Rift, basically forming it with this current going down southward. But it goes out of the southern tip of Africa and into both South America, which goes like this, and it wraps up this way and interacts with that first portion going eastward. And then it also goes into Antarctica, through it and into Australia. I can't really. Let's just hit play real quick. Which was over here by North America, because it's in an Earth expansion model. All the ocean floor didn't really exist yet, or other things. It was forming physically below continents, even the Western Pacific. And then the current went across this way, involved in the Mariana Trench there, across this way. See the pathway through here, right there, over down that way to the Mariana Trench. And then there's another one that way, up to this boundary here. So I'm tracing past, kind of deciphering which way current was flowing within them. And then it interacted with these other currents at Australia, which created this like fractal atom, which then had a decay product of a sphere. I know, pardon me, but this is the framework in which I am looking at this data through, and it matches. That's the crazy thing. We're gonna find so much evidence that in Baja, BC, because as we go forward here, it basically, this current down this way, I'm not exactly sure. I think it goes across and interacts with the one under North America here. This is basically coming out from under North America right here, interacting with it, and then it induces this structure here that's like a magnetic field, like a figure eight structure, a vortex, which then has a jet stream in the magnetic anomaly map going northward that does this right here is what I'm saying is highly related to everything we're gonna watch in all of these videos, is highly related to this process going on right here. Right here. Which goes up this way. If I go like this real quick, notice this point here. So that's what I was saying is Western Pacific was physically below North America, where the mid-Pacific mountains were forming physically at this region below North America against its resistance, which is this here. Was forming against it, but then this current continued upward. I'm not sure if it went this way. I've been noticing evidence that it might have actually went through this region exists, which we'll maybe try to decipher as we go forward in terms of what exactly is happening. Probably both, honestly. But certainly there's evidence of current flow going in this way into internal North America. I don't know if it may be hard to say where are you looking at because this is a map. Like I'm acquainted with this map, but its boundaries are not so clear where we're looking at. Here's Florida over here. Here's California. This is North America. Here's Vancouver. So Baja, BC accretions were brought by the jet. So maybe it's worth real quick noting. So this structure generally. Here, I was looking at this. Just noting one of the aspects of Baja BC is this concept of a hit phase and then a run phase. So it like hits, gets lodged there, basically stays there from 100 million radiometric dating to 85, and then 85 to 55. According to this slide, I'm not sure. We'll look at the papers going forward more closely. It moves northward, at least the insular and intermontane terrains. And I recently, the last episode or so, I don't even think I talked about this yet in my underground science videos actually, but generally have been coming to become aware that this is something related. Let's go to this slide. Let's go to that animation. Ontong Java. So Ontong Java Plateau is here. Manihiki Plateau is over here once this fades back in. Oh, there it is. There it is. I guess I messed this one up. There's Ontong Java. There's Manihiki. I don't know why it's all like blurry color. But basically, this trident structure here coming out of the top goes over to the side and bends upward at this final point going up to here at Manihiki, and then it goes over this way to here. Just kind of to the boundary of Ontong Java, but I think there's more going on with that one than Manihiki over here. And then there's another one, Hikarangi Plateau. It's south by east of New Zealand, which is in a theory of the Ontong Java Nui, where all three of them, Ontong Java, Hikarangi, and Manihiki, formed as a single unit, and then they divided. So notice these dates, 125 to 120 million, breakup 118 to 86, and then evolution, meaning motion, like they moved apart from one another from 86 to 80 to 40. These dates are very Baja BC dates. And basically what I'm saying is here's Ontong Java Plateau. Don't mind this line for now. We'll get to that at some point, hopefully. This Ontong Java Plateau, this oceanic plateau, that is a large igneous province, which is one of the things in my last 10 episodes, has been very focused on this. So if you want to know more information about these and my interpretation of these, my last 10 episodes or so since 360 onward, 361 has really loud music, but has closed caption is functional on my videos at this point somehow. This is Hikarangi down here. Basically, this trident thing went between it, divided it. It's physically a current, this here. It's physically a current that goes through and then wedges open, spacing them apart, but as it flows through, it goes up and through this region before it moves. Because essentially this right here was all the way over here at the time because the earth expanded. This was over there. Sorry, I know there's a lot of like weird things that maybe are off-putting enough to not even bother to watch this reaction, but it's really essential to be acquainted with where I'm coming from as I react to the rest of this, because like I'm legitimately discovering things in my, like, it is what it is. These were over here. Papua New Guinea was like physically connected to that point there. This point, this region of Papua New Guinea was connected there to the ocean. Notice the ocean floor. Notice these two are very much like one another. They were adjacent. There's even like actual paths between them. And then Philippines were up here. This one's not in the right angle and out of place and other things probably. But those were there. Australia was adjacent to all three. Like this. Ignoring this portion there, basically. This is more as it actually was, with the extensional arms that come off of Borneo going around the Philippines that then separated, but are attached to Borneo still. But these were like this along the side of Australia, and I've gone into the oceanic plateaus over here and all throughout the Pacific and found really interesting parallels to this line of reasoning and the actual nuanced data, especially this one. This one's incredible how well it demonstrates Exmouth Plateau there, how well it demonstrates, or mouth, I don't know. I'll just say words, I don't know how to read on paper. Just that there's merit to this current, this jet stream going up this way, through this way, and influencing this whole region. Okay, so the first paper by Beck and by Nosen. So Merle Beck and Linda Nosen are co-authors of that one. I didn't realize when I said that. Otherwise, I would have said Beck and Nosen. I thought it was just a Beck paper. But they're co-authors of this. This was a short one. So let's real quick go through this. Large northward translations of portions of the Western Cordillera is basically some things are pointing to that. Anomalously low paleomagnetic inclinations in radiometrically dated batholithic rocks exposed in the Cascade Range of central Washington. So paleomagnetic inclinations. Results suggest that these rocks originated roughly 25 degrees further from the Cretaceous pole than their present location relative to North American cratons suggests. These are, I'm not sure where they're talking about exactly, in Western Canada, I guess. I said, perhaps it is worth noting that there are locations that have great variation in magnetic stability where repeat measurement causes erratically changing directions determined, and that this tends to be a common characteristic of granitic rocks. So they did 5 different sites, 3 of which show high magnetic stability, so they're useful pretty much. One site is marginal but non-random, so there's some degree of use for that one, and another is completely unstable. Why exactly that is, I don't even know what to make of it yet. That's the first I really came across that kind of concept in all of this. Sample, at least that I like remember. Maybe I heard it in passing, but samples from Site C, a leucocratic granodiorite, change direction erratically on repeat measurement, so they can't use it to determine where the North Pole was, like back calculate where was this pole at the time this formed, because it's very erratic and it's just not useful in that way. Maybe in other ways, but not in that way. No evidence of stable magnetic directions was found in Site C. The great variation in magnetic stability found in this study among rocks of similar origin and appearance is puzzling, but appears to be a common characteristic of granitic rocks. So I just noted that. Mostly is why I posted that one. A mean Cretaceous pole for North America. This is generally North America has a mean, like the average mean Cretaceous pole, the pole that North American rocks point to the North Pole in the time of the Cretaceous, which is not the same as now necessarily, at least, points to 68 degrees north, 172.3 degrees west, the mean. Whereas, and then they just kind of go into detail of all the places that point to 69 degrees, 175. So it's basically several different methods or locations across the North Pole or North America, New England, Quebec, California, Wyoming, Utah, give poles that are near each other. This type grouping is strong evidence for the existence of a dipolar magnetic field during the Cretaceous time, and further suggests that the Cretaceous was a time of little or no polar wandering. So like a very, that's the pole kind of time frame. The pole's not moving around really. It's pretty solidly a certain location, generally around where these things point to, at least according to North American rocks. Poles for stable sites in Cretaceous granitic rocks from central Washington lie far outside the cluster of poles for the remainder of North America. According to their next figure, I didn't bother to do that figure. Where's figure 2? Here. I believe E is the other side. I'm not sure. Let's just keep going. Stevens Pass area. I'm not sure exactly where that is. It's been hours and I already forget like specifics. Let me just read over here. It further describes 20 to 25 degree differences in calculated paleolatitude and possible causes, such as a period of anomalous behavior of the geomagnetic field of the Earth, saying such breakdowns must, however, be rare and are particularly unlikely for the Cretaceous. So let me just read this now. This difference in paleolatitude here corresponds to a difference in inclination of remnant magnetization of about 20 to 25 degrees. Undetected tectonic tilting could thus account for the apparent paleolatitude anomaly. So, like, we find the rock in place somewhere and take a sample of it, but if the rock has tilted, then it's possible that that tilt makes it look as if the magnetic field was pointing at a different angle. So they said is possible, could thus account for the apparent paleolatitude anomaly. Deformation would presumably be easy to detect, but has apparently never been reported. So this is like pointing away from such a cause of like this tilting. The difference might also theoretically be the result of a period of anomalous behavior of the geomagnetic field. So it could be that the pole was wandering around rapidly and that one captured a distant pole to nearby but different time structures where it looks as if it moved 3,000 kilometers, but maybe it didn't, kind of thing, such as the short period of geomagnetic fluctuations tentatively invoked by Spall, which I probably should look at that one too, to account for anomalous paleomagnetic directions in Mesozoic dolerites from Spitsbergen, which is over here. Over here. I didn't know what to make of it exactly. But I did look up where I was just out of curiosity, but I really need to read the paper. I did look at an extra paper actually. Such breakdowns must, however, be rare and are particularly unlikely for the Cretaceous in view of its strongly dipolar magnetic field. Beck describes north and no sun describe northward relative motion of as the favored explanation. My words, I don't know why I emphasize favored. Maybe they say favored too. The locus of possible poles of rotation of the Stevens Pass area relative to North America passes close to Morgan's pole of rotation of the Pacific Plate. It may be fortuitous, they said. Whenever there's something of that nature, I pay attention to. So let me just read this over here now. If the Stevens Pass area and contiguous parts of the Western Cordillera were originally part of a separate plate and were therefore free to move relative to North America until Cretaceous time, the observed paleolatitude difference might easily be a consequence. In this model, relative motion of the two continental masses ceased, and welding of the two to form one continental landmass occurred at some time in the Tertiary. So tertiary, 66 to 2.6. I think that by 40 million, though, this is kind of seizing this process. So it's probably more like 66 to 40 million radiometric dating. Shows the locus of possible, the figure we just looked at with the dots on it. This one shows the locus of possible poles of rotation of the Stevens Pass area relative to the rest of North America. Based on our sparse paleomagnetic data, this locus passes close to Morgan's pole of rotation. So this is the other paper that I did look up. So at the end of this, we get to Morgan's pole, which is just another pole suggested by fracture zones. Basically, someone drew circles using these fracture zones as a to try to like put the circle over top of it, and then looked at the center of those circles and found it was like over like here. It's like over here. Something like that is Morgan's pole. It's just another location over here, somewhere maybe over there. But I didn't know what it meant at this point, so it's useful at least to be aware as we read the sentence. Relative pole of rotation of the Pacific plate relative to the North American plate, but this may be fortuitous because according to Atwater, who keeps coming up, and that's the one I mentioned that would come up earlier, that I did a video 370 of underground science. I read one of her papers. According to Atwater, the Kula and Farallon plates should have prevented any interaction between the Pacific and North American plates at the latitude of Seattle. I don't know in an Earth expansion model if the totality of these plates, like there's something up with these plates that I haven't researched enough. I should probably look into them more. Should have prevented any interaction. So, like, if there's interaction between the Pacific and North American plates at the latitude of Seattle, with this apparent plate between it of the Kula and Farallon plate, maybe it's because the Earth expanded. And we're just like interpreting plates, like portions of plates that are subducted, and we see like the more recent portion that once they separated, but maybe at the time they were actually physically together enough that they did rotate together, so that it's not that fortuitous. But at the same time, Morgan's pole, I don't know what to make of it because it's very plate tectonic framework, and maybe, I mean, it certainly points to some things, but probably is missing a lot of key nuances. Mind you, these are from 1972, 73. I think that one's from 68, the Morgan's pole. So they're pretty old papers. There's probably a lot of subsequent work afterwards on them, on their topics. There's certainly a lot of subsequent work on Baja, BC. Like this is just noticing that something's up. That's what's going on in these papers. They're like, something seems awry here. We don't know if it's because of motion. Seems like it's because of motion, though. Maybe it could be rotation. Like, perhaps the Stevens Pass area once moved as part of the Kula plate. The estimated velocity of the Kula plate relative to North America in a generally northward direction, which again, if we that made me say maybe the Kula plate is really related to these current flows going this way that we're also over here, like pushing against North America, maybe spacing the Pacific plate. That was physically, in my interpretation, the Pacific plate, maybe it's worth seeing this, was forming like this, literally under North America and under Australia. Australia was like here, and it slid out from under, and then at some point a physical gap was between, but maybe it didn't even need the gap. Like it just by sliding, it opened space for other currents to flow in, which then ended up being the Kula and Farallon plate currents that then slid out too in part. I'm not sure. Stevens Pass area could have increased in latitude by 25 degrees in as little as 25 million radiometric dating. Because according to Atwater, yeah, so I just said essentially what I just said. So let's go on. Second paper. This is Linda Gianna Nosen, who was the co-author of the previous paper. This is her thesis. So it's pretty long. I did read it in its entirety, although there's a couple sections that I was like, something I don't have to quote. Like, how to do paleomagnetic measurements. I don't really care. I trust you on that one. Like, I mean, so a paleomagnetic study of 3 granitic plutons exposed in the Cascade Mountains, Washington. So Cascade Mountains. Oh no. Over here in this area. So specifically Mount Stuart. So this one up here. And there's some images, but let's just get going. Paleomagnetic data from the 3 age-dated granitic plutons. Samples from the Mount Stuart Cretaceous, Grotto Miocene, and Index Oligocene batholiths of the North Cascade Mountains, Washington, were collected. Analysis of the paleomagnetic data resulted in the elimination of all samples from the Index batholith due to unstable magnetization. Interesting. In the Oligocene. Wonder if it was like the pole was vibratory then? Or if that's just something else. Poles were determined. And then there's the poles, Mount Stuart, and the Grotto batholith. Comparisons of these paleomagnetic poles to paleomagnetic poles of similar ages from other locations in North America, like the previous paper was doing, resulted in the following conclusions. Since the Miocene, paleomagnetic data from the North Cascade Mountains of Washington indicates insignificant vertical or horizontal displacements between the Grotto and Snoqualmie batholiths, which are related, and the rest of North America. So basically, since 26 million, there hasn't been any difference in the paleomagnetic data. These poles point to the same place as anywhere else in North America is generally pointing to, is what it essentially. Whereas the Cretaceous Mount Stuart paleomagnetic pole differs significantly from the average Cretaceous North American pole, indicating either large-scale translation about 30 degrees latitude or rotation about 25 degrees of the batholith relative to North America. Or maybe both, but really probably if there's any translation, then it really opens a huge door. So I imagine that's kind of why they said one or the other. I'd imagine though it would be a little bit of both. So maybe like slight. I don't know. Let's keep going though. Just trying to entertain the possibility that there's a little bit of both in my head, although I'm pretty sure it's almost entirely translation. Until more paleomagnetic and geologic data are available from the area, these two alternatives are inseparable. So it could be either in 1973. It could be either. Yeah, we're probably gonna have to do 2 parts per episode, it looks like. I mean, let's be real. The Cascade Range, trending south to north from California to southern British Columbia, consists of a pre-Devonian through Mesozoic basement complex overlain by tertiary volcanics and sediments that are intruded throughout by late Cretaceous to Pliocene granitic magmas. So basically, it has this basement that sometimes is visible. A broad structural upwarp parallels the axis of the Cascades, bounded on the west by this trough, which I don't know anything about and I'm kind of curious about, and on the east by the Columbia Plateau, which I guess is just generally over here. Increased vertical relief from south to north along this structural upwarp. So south it's not as elevated, uplifted as north. And the contrast between northwest southeast trending pre-early tertiary, so before the tertiary, I guess. So like Cretaceous. In the Cretaceous, there was a northwest southeast trending aspect of the upwarp, I guess, in the Cascade Range, and later it became a north-south trending regional structures. So there's this uplift shifting its direction in the Cretaceous to the tertiary. Maximum uplift in the northern Cascades provides excellent exposures of the Paleozoic's basement rocks dating back to the Paleozoic and Mesozoic rocks that are generally obscured by overlying tertiary volcanics further to the south. Two distinct Mesozoic orogenies recognized in the Cascades are recognized in the Cascades. The older episode involved widespread regional metamorphism and deformation, and the second Mesozoic orogeny was typified by lower grade metamorphism and strong deformation that produced large scale overthrust faulting to the west and small scale overthrusting to the east. So that's interesting. That kind of going back to that concept that the current actually went in this way. So like there's a pressure more so westward, which would seemingly produce large-scale overthrusting faulting to the west and smaller scale to the east, because it's still kind of moving through things and creating faults, but it's just got like a slight westward force, mostly north, but slightly west, so that it like more so applies pressure westward. The major post-metamorphic faults separating the units of the Cascade Metamorphic Suite originated during the second Mesozoic orogeny. Westward displaced Schucksen thrust of probable mid-Cretaceous age separates the Schucksen Metamorphic Suite on the east from non-intruded rock units to the west. Well, that kind of non-intruded rock units to the west. Maybe I don't know enough about this area to really draw conclusions. That kind of counters what I was just saying, just at first glance, but maybe. North-south trending Ross Lake fault of Middle Cretaceous to Late Cretaceous age. Anything in the mid-late Cretaceous, I'm very much like, because that's really when the Earth expanded. Like, until late Cretaceous, the Earth was not rapidly expanding. It was just building up pressure, forming underlayers. Literally, the entire Western Pacific, like I was showing there, was forming underneath the crust, but the continents did not move, so that they didn't break apart until late Cretaceous, at least not enough for the Earth to expand and the oceans to form as we know them today. It wasn't until late Cretaceous. The mean age of oceanic crust is 64.7 million. The mean age of the Pacific is 66 million. And that's because the Earth expanded rapidly in the Cretaceous, at the end of the Cretaceous, because continents actually broke apart from the internal pressures of this undercurrent that was just filling coming out of the mantle, and for reasons that are hard to explain in short, and just flowing in all directions from specifically one point in Pakistan, but in all directions. That then created the overall magnetic anomaly map as we see it today, is like its stable end result. So anything that's talking about that, the north-south trending fault separates metamorphic rocks from the eastern metamorphic zone of the Cascade Metamorphic Suite. It is a westward dipping, high angle reverse fault, probably with some component of right lateral strike slip movement. I'm going to really try to just read through this because, and just talk about anything that I really am drawn to, because there's just so much more to go through. I pretty much am going to read her entire thesis, so I gotta get going. It was like 37 pages. This major crustal discontinuity has been the site of repeated granitic intrusions from the late Cretaceous to Tertiary time. Strait Creek Fault separate. I don't know why. I was just kind of underlying. This is more of this context of where we're at. Strait Creek Fault separates the western Shuckson Belt from the central Skagit Belt. This steep eastward dipping fault is typified by considerable right lateral strike slip movement, possibly beginning during the latest Cretaceous and continuing into the Eocene. In addition to faulting, vast amounts of flood basalt were extruded during the early to middle Eocene. From Oligocene to the early Miocene, stocks, I'm not even sure what stocks are, and batholiths, such as the Index and Grotto batholiths, were emplaced along the length of the Cascade Range. Other than broad epeirogenic uplift that began gradually in the Miocene and culminated during the Pliocene to early Pleistocene periods, tectonic deformation following the emplacement has been insignificant. Let's look up that word. Epeirogenic. Upheavals or depression of land exhibiting long wavelengths and little folding apart from broad undulations. Reminiscent of the Great Basin, I guess. So other than broad undulations that began gradually in the Miocene and culminated during the Pliocene to early Pleistocene. Let's look at that. very much, okay, pointing to a similar process going on in the Cascade Range, but basically insignificant deformation after these were in place. These demonstrate to us that there was very little deformation after that, because they themselves only have these types of deformation, really. And then here is a index to the map on this right here. Here's Mount Stort batholith. Just kind of strangely shaped, interesting. Let's go back real quick. Metamorphics, mostly pre-Jurassic. So pre-Jurassic metamorphics. Pre-Triassic basalts. Pre-Jurassic metamorphic. And then there's the grotto batholith, index batholith, and the Snoqualmie batholith. So there's some relationship between two of these. I think the grotto and the Snoqualmie, where they're pretty much the same source but different radiometric dating ages. Considered to one's, I think this one's younger. Maybe that one's younger. I don't remember. So there's that one. Some additional details on the index. Index, Snoqualmie, and grotto batholiths. There. Okay, here we go. The plumber mapped the area between the index batholith and the Snoqualmie batholith. His work supported the conclusion that the index batholith was a subdivision of the Snoqualmie batholith. Later on, Erickson examined the Snoqualmie batholith, aided by radiometric age dates, and concluded that the index of index batholith and Snoqualmie batholiths are actually separate intrusions, so they're not basically the same batholith. The grotto batholith, texturally and mineralogically, is similar to the index batholith. It has been correlated with the index granodiorite, the Snoqualmie batholith, and the Snoqualmie batholith. Because of the petrographic similarity of the index and grotto batholiths, Yeats gives a combined description of their petrology and petrography. Radiometric age dates indicate that the grotto batholith is a younger Pluton than the index. Almost makes me think of like pillow lava, pillow basalts, like bloop, 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 like blobs. I don't know. Obviously they're not, but it just kind of gives me that thought. Beckler Peak stock is a coarse grain. So this is a part of Mountain Stort. So before we read on, it's worth knowing that is a coarse-grained, weakly gneissic quartz diorite, probably emplaced as a crystal mush. I don't know what that means, but like Mount Stort is probably a part of a crystal mush. Is a movement of the stock to the southwest and upward is suggested by the northeast dip of the western and eastern context. So I found that kind of interesting. In all of this motion, there's a southwest motion too. Stock is bounded on the east by the Evergreen Fault, and is a subdivision of the Mount Stort batholith. Recent radiometric dates support this hypothesis. Beckler Peak stock, therefore, is referred to as part of the Mount Stort batholith. So I'm not sure what the Beckler Peak stock is. It's just an older interpretation of another portion of the Mount Stort batholith. Biotites Dating the batholith indicates Mount Stuart is of early late Cretaceous age, with index batholith of Oligocene age and grotto batholith of Miocene age, based on a combination of geological evidence and radiometric dating. Biotites from the index batholith dated to 35 plus or minus 5 using strontium, whatever, age of 40 plus or minus 2 from biotites collected from the index batholith. So some variation. Later resampling using potassium argon ages 32.5 plus or minus 2.5 using hornblende, and 32.5 plus or minus 1.2 using biotite, which is a hornblende forms in the presence of water. I don't know, worth noting that, I guess, considering the circumstances of this. These age dates are compatible with geological evidence, which indicates that the Pluton was intruded into late Cretaceous Paleocene Swalk Formation, which I do believe comes up again in Nick Zentner's videos, possibly as an entire episode, and possibly into Eocene volcanics. The grotto batholith has potassium argon ages of 26.3 plus or minus 0.8 using biotite, 25 plus or minus 1.5 using hornblende. A combination of geological evidence and radiometric dating indicates Oligocene age for the index batholith and a Miocene age for the grotto batholith. A definite time interval elapsed between the emplacement of early tertiary plutons and the older Cretaceous plutons. So these are early tertiary. Biotites from the Mount Stuart batholith, which is older Cretaceous pluton, which is unconformably overlain by late Cretaceous Paleocene Swalk Formation, has been dated to 94.2 plus or minus 16 million years radiometric dating. This person gives fission track ages for the Mount Stuart of 91.7 and 83.0 plus or minus 2. The Mount Stuart batholith by this evidence is of early late Cretaceous age. So early on in the late Cretaceous, in the time frame of 80, 90, 95 million, 100 million radiometric dating, is the Mount Stuart batholith. Then there are several pages discussing the method, reliability, and the like of determining paleomagnetic data, followed by a plot of paleomagnetic poles for each site. So here's the poles. Here's poles. Let me go to this one. For some reason I put this at the end. Grotto batholith is 1, 2, 3. Snoqualmie is S1, 3, 4, 6. Mount Stuart is 4, 5, 6, 7, 8. So here's the Mount Stuart batholith. So basically the mean average of the Mount Stuart batholith is all the way over in Siberia, just about, where the mean, not each, but the mean pole of the Mount Stuart, and then of the other ones, this is the other ones, 1, 2, 3, S1, 3, 4, 6. The mean pole of these is really kind of the North Pole, which, as they've mentioned, these don't show the evidence of moving, where the Mount Stuart really is the only one that has that evidence in this study. Then I said, it is worth noting the Cretaceous pole is near the position on the magnetic anomaly map where undercurrents flowed into Eurasia, while the Miocene-Oligocene pole data point to the modern pole terminal location of the magnetic anomaly map. So I've been calling this like the North Terminal. They point generally to there, where The Mount stored area is over here. I don't know what to make of it in this sense. I think this is kind of moot in some way, but in other ways, maybe not. I'm not sure. I just thought it was interesting because this region is really important, and there's even like a, if I go over here. Like there's almost like a structure there that kind of mimics the actual map of this. Like if you look over here, it goes to the middle of Sweden and Norway. Over there, I mean, the map is not that clear on where it is. But the middle of Sweden and Norway, so it's like this edge is kind of the middle of them. There's Norway, or is it Sweden? And Sweden. Like it kind of goes to the middle of those. And then it kind of goes over here to like, I don't know. I just thought, I was like, that's weird. I don't know what to make of it, but I'll just kind of mention it. Nosen describes interpretation of possible causes of the variation, ruling out viscous. So instead of reading this, let me just kind of skip through this. Or should I? Let's just read it real quick. Let's not do any injustices in the actual like important things. Mount Stork batholith. The difference between these site mean directions of. Alright, I don't know why I didn't underline that. The direction of magnetization with respect to sites within the Mount stored batholith appears to have been consistent throughout the intrusion. Site mean directions. Oh yeah. This is something to do with the method of measuring the direction, like a more, like it should be like kind of a cone, like some of them point this way, some of them point a little further, and then there's like a cone that they point to, and the site mean direction is, I believe, like the center point. Difference between these site mean directions using different methods, I guess. The direction of magnetization with respect to sites within the Mount Stork batholith appears to have been consistent throughout the intrusion. Hence, any tectonic movement affecting the Mount Stork batholith must have either involved the entire batholith or affected its parts equally. So, like, it must have moved entirely as a single unit. Doop. Or basically moved as parts, but all moved to the same location, one or the other, so that they're all affected equally. Grotto batholith similarly retains a uniform direction of magnetization, so these are useful. The other one doesn't. Site mean direction from the younger Snoqualmie batholith exposed to the south near Snoqualmie Pass are insignificantly different from those of the Grotto batholith. Major relative tectonic movement between the Grotto and Snoqualmie batholiths therefore appears unlikely. So those don't seem to have moved much. The mean paleomagnetic pole for the Mount stored batholith and the Grotto batholith can be compared to the poles of like ages located relative to other rocks units in North America. I mean, we're kind of like rereading the same things, but a little more detail than the abstract and so on. Comparison of the mean paleomagnetic pole for the Grotto and Snoqualmie batholiths with other tertiary poles from North America, including the Eocene, Granite Falls stock of the North Cascades, shows statistically insignificant variation in location. Any major tectonic movement between the Central Cascade Range and Cratonic North America would therefore have had to occur before the Eocene, 40 million. The mean pole for the Mount Stort batholith differs significantly. This discrepancy could be caused by one or more of the following. So this is way more detail now. Here's some options: viscous remnant magnetization, secular variation, non-axial behavior of the Cretaceous geomagnetic field. So like it's moving around. Resetting of magnetic directions or radiometric clocks, or both, by some mechanism. In situ block rotation and translation. So viscous remnant magnetization may be superimposed on the primary remnant magnetization in the presence of the Earth's magnetic field at temperatures lower than the Curie temperature. Magnetic domains with low coercivity may be realigned by subsequent changes in the geomagnetic field. So basically, in some instances, changes in the geomagnetic field can realign the magnetization. Demagnetization, however, should randomize these low coercivity domains and thus destroy the contribution of viscous remnant magnetization. The pole of the Mount Stort batholith is distinct from the present magnetic pole, which, if viscous remnant magnetization is occurring, it should not be distinct from. So because it's distinct from the present magnetic pole, it indicates the negligible influence of viscous remnant magnetization. That one. Secular variation. Was it that one? Option 2. So option 1 they rolled out, and not that one. Secular variation occurs as fluctuation in the magnetic field in any one place by an order of magnitude of 10 to 20 degrees. So just some local fluctuation in the magnetic field. This regional phenomenon has probably contributed little to the dispersion observed between the mean Mount Stort pole and other North American Cretaceous poles. The widely separated sample sites, meaning not so local, may differ in ages by about 10 to the 7 years, which is million, or 10 million even, maybe 10 to the 7. You can figure it out, I don't care. The slow cooling rate of plutonic rocks likewise would seem to provide ample time to average the effects of secular variation. La Rochelle suggests that secular variation in the Cretaceous was less than at present, and present-day secular variation itself is probably too small to account for the observed anomalous position of the pole of the Mount Stort batholith. So they kind of roll that one out too. Anomalous Mesozoic magnetic directions have been explained by from that one place we were looking at over here, have been explained by postulating a short period of geomagnetic fluctuations and the breakdown of axial dipole field. Let me just real quick. Let me just right quick go up down here. It was Spall. Precambrian. In the pre. Okay, I just wanted to kind of pull that up. It sounds pretty interesting. But agreement between paleoclimatic evidence and the proposed paleo, well, I don't know exactly what that means, but I'll take their word for it. The proposed paleo latitude of 30 degrees north for the Mount Stuart batholith suggests that the Earth's field may have had the form of an axial dipole, meaning it wasn't wobbly, fluctuating like wow. Moreover, the close agreement between North American Cretaceous pole positions other than the Mount Stuart batholith likewise suggest the presence of an axial dipole field. So it's stable. The North Pole, South Pole. Stably positioned. Not, wow. The first half of the late Cretaceous was probably a time of magnetic stability. So the possibility of anomalous geomagnetic fluctuations appears unlikely during Mount Stuart's formation. Determining the sequence of geological events in the Cascade Range is complicated by repeated episodes of regional metamorphism, tectonism, and plutonism. Regional metamorphism of these places, Skagit and Shuxen suites, may have occurred during the late Permian, early Triassic. Even low Cretaceous age dates have been recorded. The Shuxen thrust, which is older than sediments containing late Cretaceous Paleocene fossils and younger than Skagit, Shuxen regional metamorphism is tentatively assigned a mid-Cretaceous age. Radiometric age dates, therefore, should be used in the conjunction with other geological evidence. The absence of major metamorphic or orogenic events following the emplacement of the Grotto and Index batholiths reinforces the validity of their radiometric age dates. So I guess number 4 is kind of like by using the wrong age and therefore like relating it to other North American things of the same age as the wrong age would point to a different pole because the age is wrong. I guess that's kind of what they're ruling out. I didn't quite understand it reading it the first time because the list itself didn't seem to read like that. Like this here, resetting of magnetic directions or radiometric clocks. Now it kind of makes sense. Now it kind of makes sense. So like they're ruling out that there's some major discrepancy in the age. Sequence of events surrounding the placement of Mount Stuart batholith are less easily defined. Radiometric age dates indicate an early late Cretaceous age for the Mount Stuart batholith. So it's still good in that regard. The dates for the Mount Stuart batholith are considered to be highly reliable, so the dates are good. Now we get to the two options that are actually feasible as of the writing of this paper. The displacement of the Cretaceous Mount Stuart pole away from the mean Cretaceous pole relative to North America could be accounted for by a rotation of the entire Mount Stuart batholith north side upward until the inclination of the site matched that observed. The difference in inclination would be approximately 25 degrees, which could possibly be achieved by pervasive block faulting. While evidence of such deformation in the Mount Stuart area has not been published, Souther suggests profound uplift during the late Cretaceous in nearby western British Columbia, accompanied by extensive high-level plutonism and block faulting. Since so nearby, there's these potential ways in which Mount Stuart could be angled 25 degrees off of what it actually was. when it formed, but in position that it formed. But they're nearby, but the evidence is not actually found at Mount Stewart itself, just nearby. Other evidence suggests that large-scale translational movement between the Cascades area and North America may have ended by the Cretaceous. An explanation of the discrepant pole position by in situ block faulting is further supported. This evidence includes an association between Jura-Cretaceous Tethyan ammonites and boreal ammonites, which I found interesting because it's ammonites, belemnites, and buccias that occurs in rocks exposed in western British Columbia suggest intermixing of Tethyan and boreal faunas possibly as early as Jurassic. I don't know what to make of that, but so be it. Simons suggests little or no movement of Vancouver Island relative to North America since the mid-Jurassic, 159 plus or minus 10, but suggests large displacement. So this, going back to that, Vancouver Island is here. I believe it's this whole thing. And here's the Cascades region. So if this didn't really move since the mid-Jurassic, I don't know if that's the current interpretation. I know there's episodes in here. Possibly the Nanaimo group with Jerome Lessman. Okay, let's keep going. The stratigraphic record, so another possible rotation explanation. Stratigraphic record and continuity of structures related to Mesozoic tectonic events along and across the Cordillera. Structural trend as evidenced that the insular belt, coast crystalline belt, and the western part of the intermontane belt of British Columbia have been in their present positions relative to one another since the late Triassic time. I'm not sure if that's modern interpretation of things. Insular belt, intermontane belt. I'm pretty sure that's out of date. This here. I might be mistaken, but I'm pretty sure that's just out of date. The limited above evidence indicates that in situ block rotation. I mean, at this point, the data is not pointing to this, but in 1973, it was an option. So, in terms of rotation, it's really pointing to motion, the translation from Baja to British Columbia, Baja, BC. Okay. Thus, the limited above evidence indicates that in situ block rotation of the Mount Stewart batholith, rather than large-scale translation, may have caused the observed dispersion of the Mount Stewart pole relative to the Cretaceous pole for North America. If so, the magnitude of the rotation should have produced a tectonic pattern that can be detected in the field, which is another reason I think this has been rolled out, because they've looked for these things. If one assumes that the inclination observed within the Mount Stewart batholith has been insignificantly affected by rotation, then the anomalous pole position could reflect a change in paleolatitude of the Mount Stewart region relative to the rest of North America. This is already an hour and a half. Almost. I'm just like, oh. Is it feasible for you guys? Let me know. Maybe if anyone who watches this and has gotten to this point, like, if I should be doing this or just jump into the reaction itself to this, because we haven't even hit play. And this is a reaction video. It's just not reached it yet. Let's see how many. we're getting there, but if one assumes, did I read this? Let's just read it again, I guess. If one assumes that the inclination observed within the Mount Sort batholith has been insignificant and affected by rotation, then the anomalous pole position could reflect a change in paleolatitude, okay, about 26 degrees. The paleolatitude relative to the average Cretaceous pole for North America would be about 57 degrees, a difference of approximately 30 degrees that corresponds to a distance of about 3,000 kilometers. Baja, BC. So that, like, this is the first mention of the sheer breadth of the distance. This explanation of the anomalous Mount Stewart pole is compatible with faunal evidence of possible large-scale post-Permian Triassic translation. So maybe I should pause here. I just had a thought. Something that might be worth showing. If I can quickly find it. I think it's in here for some reason. I don't know why I put it in here, but it's right here. So like there is the angel thing is here, going up this way. Through currents are going up this way. Okay, I don't know why. I just thought I'd kind of. Oh yeah, that's right. Because we're talking. Here's Baja. It's almost like it folds out. Like this side starts moving away. This stuff starts moving away, and this angle starts going that way. I mean, this thing, this whole area forms, I think Zealandia, for instance, is like 85 million radiometric dating when it's formed. So it's certainly forming in the same general time frame, but I think it's all kind of ballooning from this region. And they're swirling, which is, I mean, look at Fiji. It's literally like a spiral, like spiral armed galaxy kind of looking thing going on there. Okay. This explanation of the anomalous Mount Stewart pole is compatible with faunal evidence, paleomagnetic evidence of translation of the crust of the Pacific Ocean in the western margin of the Cordillera northward by several thousand kilometers relative to North America since the Triassic. Paleomagnetic study of Pacific seamounts indicating about 30-degree northward movement of the Pacific plate since the Cretaceous. The presence of large-scale post-Triassic faults, the Mount Stewart, along which translation could have occurred. The faults along which translation could have occurred. The Mount Stewart batholith could have been a part of the Kula plate that subsequently became welded onto the continent at the present site latitude sometime during the early Tertiary. Sometime prior to 40 million years ago, radiometric dating. A tentative locus of possible poles of rotation of the Mount Stewart batholith relative to the rest of North America passes close to Morgan's pole of rotation of the Pacific plate. So that's the pole we already talked about. That's based on circles that match with the fracture zones. These lines. Which we'll get to the paper pretty soon, actually. There it is. Although proximity to Morgan's pole may be coincidental, it also suggests the tenuous revision of Atwater's diagram seen in Figure 9, which I believe I just put there because I underlined this. In this case, the Mount Stewart batholith may have been a part of the Pacific Plate. Although the paleomagnetic data obtained for tertiary granites in this study indicate stability between the central, so this is, I guess, still going on that post. Stability between the Central Cascades and the rest of North America since the Eocene, enough time may have existed for northward movement of the region as a part of either the Kula or the Pacific Plate. Perhaps the absence of granitic rocks in the Cascades within the interval from late Cretaceous to Eocene reflects this period of transform motion. I don't know if that's valid, but I found that interesting regardless. Okay. Then here's the table of all of the Cretaceous pole positions that were used. Mount Stewart is K1, notice K1, and then Canada, somewhere in Canada, Northwest Territories, Quebec, Vermont, Sierra Nevada, California, Montana, Quebec, Montana, mean pole, and then this image, so notice they're all clustered over here. Kind of like right between Russia and Alaska. Interestingly, not at the modern pole location. Like they're clustered over here and not here. It makes me wonder if like this mass kind of reformed over there, literally. Because this is Cretaceous. They're all pointing over here. Or maybe it's, I don't know. But Mount Stewart, though, is pointing all the way over there. And then here's the image that I just included because I underlined it. But motions, motion. Here's LA, here's Seattle, kind of the area we're looking at. 80 million coming along. And then there's, I feel like the Farallon plate almost unequivocally is related to this. If I can zoom, here we go. Why can't I ever make it rotate when I want it to rotate? Unfortunately, this is not at the right angle, but here's the mantle puncture hole, and here's Gujarat, India. Here's India. So we're kind of sideways. I can't rotate this very easily for some reason. Maybe, unless I do this. Let me just do that. Okay, now we're looking at it more appropriately. Okay. Going eastward, a current flow goes out this way. Imagine it goes under the Pacific and then goes out below it over here. Farallon is just over there now. Disregard last then. Although maybe it's related. I'd have to look more. I thought it would be like, I was like, oh. And the Kula plate, I feel like is related to this upward jet of energy that was going northward here. but it was going up along this northward. And then the Pacific plate, the Eastern Pacific plate, I guess. The Western Pacific formed before, but then the Eastern Pacific, I guess, is still called the Pacific plate. It's all just kind of lumped together for some reason. And that filled in the space between and shoved it open, shoved the remnants of that jet up that way. So it's really up into this region at 40 million, and then it kind of stabilized. Ish. I don't know. I haven't really thought about these plates that much. Plates. Okay, then the summary. No need to summarize. I made it this far. What am I talking about? Close agreement of the Miocene paleomagnetic poles calculated for the Grotto batholith and the Snoqualmie batholith to the Miocene pole for North America and to the Eocene granite fall stock indicates that the Cascade Mountains have not undergone significant tectonic displacement relative to North America during the past 40 million years. Cretaceous paleomagnetic pole relative to the mountains stored, however, departs from the Cretaceous pole by 30 degrees. This discrepancy probably reflects either 1, vertical rotation of the entire block, or 2, vertical rotation by pervasive block faulting, or 3, which are pretty much different variations of the vertical rotation, or 3, a translation of the block from paleo latitude of about 26 degrees north to its present position. Further paleomagnetic and geologic investigation of the area is needed to determine the most reasonable alternative. Then I just said at several occasions, Nosen references Morgan's poles, and I found the paper with with its link. So here's the papers section where it's talking about the motion of the Pacific block relative to North American block. Literally, figure 11, a set of circles concentric about a pole at 79 degrees north, 111 east, are superposed on this figure. So the dotted lines are the concentric circles that circle around this apparent relative position of a concentric pole, a pole based on these circles, except for the Mendocino and Pioneer fracture zones, which we looked at these kinds of things with the Atwater paper, I believe, possibly elsewhere in that 370 video. Yeah, definitely the Atwater paper. Except for the Mendocino and Pioneer fracture zones, the concentric circles are nearly coincident with the fracture zones. The Mendocino, which, if we really look at it, Clarion is not entirely they're just for like a period of time they are, which is interesting. Maybe pointing to when that segment was forming. I don't know. And like maybe these segments over here are more related to the modern pole. Or this is just like a fun little thing to have picked up on, but doesn't have real merit. But I don't think that's true either. There's something to this, I just don't know what to make of it exactly. Because it's definitely in an Earth expansion paradigm in reality. It's just, sorry guys, it just is. The Mendocino and Pioneer fracture zones depart from the circles further west than do the other fracture zones. This departure is likely related to North America overriding and interfering with the flow of the northernmost end of the rise at an earlier date. These old fracture zones indicate that the Pacific once moved away from North America towards trenches off New Guinea and the Philippines. About 10 million years ago, this pattern changed, and the Pacific now moves towards Japan and the Aleutian trenches. So that's what that says. I don't know. Let's keep going, though. I got a couple more. Tying it into my research a little bit, which is cool. I didn't really know what, like, I've already looked at this stuff, so I didn't really, I just hadn't looked at the papers, but I've already watched the videos, so I didn't know if I'd really come across anything that I found interesting like this, but I found this really interesting. Initially I looked for that poll. I said, okay, I went like this. Here is the source of this jet. Where is it? Like, what's this location? I looked over here, 15 south, 178.3 west, or 0.5 west. Something in a like location I can do over here. And I went like this. I forget what I said, but 178. I gotta look it back. Let's say right there, 178. Or 178.5 and 14.2. Let's say 178.5 is 178.30. And 14, wait, that doesn't seem right. What am I doing? It just seemed too close to Fiji. Oh, I was probably... This is like right at where it goes east, west, 178, 14.2. I think I started like on that island there. And then I went over here and I went to 51.4 east. So 51.4 east is there, and then 68.7. It's a little tricky because it's basically it's kind of tricky. It moves so fast on the east-west up here. That's good enough. That's good enough. Done. So I basically did this. And I was like, whoa, dude. Right across the nose. Right across the nose. So mind you, if we go back here, to animation, yeah. this one. If we go back to this one, the nose. I don't know if that one's. These are a little tricky. I think I put it actually a little further in on a different one called like Florida. Let's see this one. There's the nose. Yeah, so I guess it's pretty much at the tip of Baja, California. Nose of the Mid-Pacific Mountain Dragon. Nose. This is the, notice also this line here. So that's what this is me saying, isn't that curious? I would check how it compared to the central path of the trident, so not just like a side path, but the central path, this path. This, like the center of it pointing upward, not just like the side of it, but the center of this, like, mini pole almost, pointing upward. I wonder if it was the other pole. I don't know if it would have been far enough away. But it having like a gamma ray burst kind of jet stream out of its pole that literally goes to the Mid-Pacific Mountains. Nose of it through that little feature and goes over there. Like, what are the odds? Like, if I choose the center of that structure and that point, it does not have to go through this. It doesn't have to go through this. Maybe I like moved it around a little bit, like even over here. Like, let's say I go over here. Like, it's still relatively parallel to that, but it's already off line with the nose. This from this island. So let's look at this. 14 and a third, 14.33 south, 170. Let's just try to go whole numbers. 178. $178 and then 14.5. That's good. I think that's still in line generally. There we go. Okay. So 178 west, 14.5 south. 178, 14.5 south, right there. Like it's clearly the nucleus region is connected to that. Like, what? It's almost like it retains a record of like the way that the earth was like this. Like, say it's a ball and then it kind of opens on a side. This retains the record of where it was pointing from over here up through this way. Even though it was all the way over in North America, when it shoved Mount Stewart over that way and placed it where it is, when this current was flowing over there, Mount Stewart points at the same location as this over here points at, so that they basically intersect at that pole. It's like, things like this don't have to happen. My research is full of things like this, where I'm just like, what in the... When I saw this, I was like, damn, dude. Did not see that coming. I was like, there's no way. I was just thinking, like, look at this angle. I know it's kind of sideways. Like, it goes over this way to go up to there. I knew it was kind of towards it. I was like, could it be? The other one, though, is, like, over here. So it's clearly, like, it's just not in path. Like, let's say I put it right there. Like, it's really interesting, maybe some relationship to Hawaii, but it's just not in path. Like, it's not in line with this. It's not in line with the critical things that I would look for this trident structure to be in line with. It's not. The other one, though, is crazy. So I go on and say that the line passes through the mid-Pacific Mountain, front seamount, the nose of the dragon, en route to the apparent pole location from Mount Stewart. I don't understand why this lost frame. Weird, on my viewer, it looked terrible. This looks how it's supposed to look at the end. Like, we can see here we can see Manihiki Plateau when it comes through, and notice where this bends. It's a little tricky to determine, like, the bottom side, but more so here. And there might be even one up there, like a further side one. There it is. Let's see. It's kind of like a menorah. Totally, like, not really apparent in there's no island there, really. Not like a singular one. There's whatever this one is. I don't even know what this is. This thing is in the nucleus. Wallace and Futuna. French islands, French territories. Alright, that's 2 hours. I guess there's no way I can do this. The papers, I can give the papers justice and react to the video in a single video. So I'm gonna have to do it in 2 parts. Certainly this one. That's too bad in some ways. There's no way. I mean, there are 2. This one's 2. This one's 3. This one's 1. But that one's got 2 episodes too. The D has 2 episodes. E, F. 1, 1, 3, 2, 2, 3 through 4, 1. And whatever. And has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is N about? Mount stored paleomagnetism. So pretty much what we were just talking about, just more details and up-to-date details. Oh my god. Incredible, really. Okay, I'll make this no longer. Thanks for hanging out. Thanks for watching episode 1 of, I guess, 52 plus reactions to the Baja BC videos. So there's that. Hope you found it entertaining. I mean, I think I got some interesting finds just here alone. This connection alone to me makes this video have some important information in it, but from my end, not just that's already out there. Like it's not just me reading these papers like a bedtime story that like anyone can read themselves, but it's also got this to it too, as well as just the general information that I have in this video. But like in terms of newly discovered connections between Baja BC and just Earth's expansion process, really, that one. Alright, thanks guys, peace.